Okay, so in the last video, this was our model. The rate of increase of the number of infected people is proportional to the number of interactions that we expect in a given unit of time between susceptible and infected people. And now we're going to change the model and add in one component, which is going to be that people can recover. So here's how that will work. During any given small unit of time, a certain proportion of the infected people will recover. So the rate of recovery is going to be proportional to the number of infected people. So this kind of this could be the consequence of maybe a rule like during any given hour, any given person has a any given infected person has a 0.1% chance of recovery or something like that. Then if you have 1,000 infected people, then 0.1% of 1,000 is how many you would expect to recover in that amount of time. Okay, so a proportion of the number of infected stop being infected during any given time. And we're still not including immunity. So there's still only two components to the population, susceptible and infected. So these guys who are going to stop being infected are just going to become susceptible again, possibly only to be reinfected later on. Okay, so this is our new differential equation, except S was n minus I. So now I've got it all written in terms of only one unknown function, I of t, rather than I of t and S of t. Okay, so this should be more interesting. Now the right-hand side, it's still an autonomous differential equation. So the right-hand side is still like a function of I only and not a function of t. And it's still a quadratic function of I. So let's write down exactly what it is. So I get a(n) I, just distributing that, minus ai squared minus ri. So it looks like I have an minus r all times I minus ai squared. And, maybe I'll actually pull out an I there. An overall factor of I times an minus r minus ai. All right, so now we can tell immediately what are the critical points for this autonomous differential equation. And by the way, the phased line still looks like that phased line segment from before, because it still only makes sense to have no fewer than 0 infected people and no more than n infected people. So this is the I line segment. Each point on the segment corresponds to some number of infected people that you could have. Now, so our differential equation is this, right? I prime is this. So what are the critical points? So there's I equals 0. That's a critical point, right? Because I've got this factor of I here. And then another critical point is whatever value of I makes this thing here 0. So what value of I makes that 0? Let me do a little calculation off to the side here. So it would be a value of I such that an minus r minus ai, let me call it I star, like that, equals 0. I'm using the star since that's just our convention for denoting critical points. Okay, and then solve for I star. So I've got r minus an there. So that is I star. Okay, interesting. Maybe another way of writing it that might make things more clear is n minus r over a. So r and a here are positive numbers. That's something we sort of have to declare right at the beginning here when we set up our model that r and a are both positive numbers. Maybe you could set them equal to 0 if you want to turn off one of the effects. Well, you shouldn't set a to 0 because then this wouldn't make sense. Anyway, that makes it clear that this critical point is less than n. It's n minus a positive thing. So going back here, our other critical point is something less than n and greater than 0. Well, I think it's greater than 0. Is it? Oh, I'm actually not sure. So this is going to be a yellow dot over there in my phase line segment, but I'm trying to figure out where to draw this yellow dot. So I know this is less than n. And this actually is really important. This matters whether this is positive or not. So this I star, I know it's less than n, right? Because it's n minus something. But I'm not sure, so question mark, I'm not sure that it's actually greater than 0. So going back here, it's possible that it's something less than n. So what was it? N minus r over a. It's possible that it's here, that it's less than n and greater than 0. It's also possible that it be over there somewhere, you know, like less than 0. Off of the line segment of reasonable values. Mathematically, I can take on negative values, just that doesn't mean anything for our particular model. Okay, but let's then split our analysis into two possibilities. So let me move this picture down here. Let's split our analysis into two possibilities. So there are two possibilities. We could have this I star value, the non-zero, the other critical point. We could have this be greater than 0, which is the picture here, or we could have it be less than 0. So if it's greater than 0, and actually we can write that in a nicer way, right? This being greater than 0, that's like this, that's equivalent to saying n is greater than r over a, which is equivalent to saying an is greater than r. So to say this is greater than 0 is to say that r is less than an. Okay, so if this critical point, this yellow dot here, is to the right of this yellow dot, greater than 0, in other words, if this is true, then this is our picture. This is our phase diagram. On the other hand, if the opposite is true, so where this one is equivalent to r less than an, this one would be equivalent to r greater than an. If this one is true, then our phase diagram looks like this. If r greater than an, our phase diagram looks like this. Here's 0. And that's it. So the other yellow dot is off that way, out of visibility, out of the range of even reasonable values for I. Okay, so that is pretty interesting that there are two ways that the phase diagram can actually look. And different things happen depending on which case we are in. So let's use the analytic criterion we talked about in the last lecture, not in the last video, but the previous lecture, to figure out what is the stability of these critical points. So to work that out, I should take a derivative of my right-hand side of the autonomous differential equation and take the derivative with respect to I. Then I can figure out whether I prime is going to be increasing or decreasing as I increase or decrease I around one of these yellow dots. So let me go back up here. What's an easy way to work with it? How about this way? So this is my right-hand side. I prime equals this thing. And then let me take the derivative. So I'll do that maybe off to the side over here. So let me copy down the differential equation. All right, so I just copied over the differential equation. It looks like this. And what I'm interested in is if I call this part f of I, then I'm interested in knowing about df di. And specifically, I want to evaluate it at those critical points, at those yellow dots. So let's see, df di, an minus r minus 2ai, just taking the derivative of this expression. Okay, now I want to evaluate at the two yellow dots. So one of the yellow dots is at 0, no matter which case I'm in, one of them is at 0. And the other one is at whatever this location is, but it only makes sense to talk about it in the first case. So let's do the 0 dot first. So for that, I will plug in I equals 0. So plugging in I equals 0, and I'm writing that in yellow to indicate that I'm putting in a critical point here. That's an minus r. Which, is that positive or negative? Not clear, right? It could be positive or it could be negative. Interestingly, whether it's positive or negative depends on which case we're in of the two cases, whether we're in this case or this case. So let's give these cases a better name. This is the case. So what is R, first of all? What does R represent? It's like the rate of recovery, right? If R is large, that means during any unit of time, a large proportion of the infected stop being infected, become susceptible. Or you could say recover. And if R is small, then during any unit of time, a small proportion of the infected recover. So R is like the recovery rate. So this first case is about having a small recovery rate, smaller than whatever this threshold is, which seems to be an important threshold for this setup. And the second case here is a large recovery rate. So let's call these the low recovery and the high recovery cases. Now, let's go back to here where we were analyzing the stability for 0. We evaluated the derivative of the right-hand side with respect to I at the critical point 0, and we got this. And this is going to be positive exactly when, an minus r is going to be positive when r is less than an, right? So that's the low recovery case. So this is positive in low recovery case, and it's negative in the high recovery case. Okay, so that's pretty interesting. So let's remember what happens when this derivative at a critical point ends up being positive. That corresponds to, as you increase I prime also increases. And as you decrease I prime also decreases. That's instability, or that corresponds to having an unstable equilibrium. So in the low recovery case, the critical point 0, I equals 0, is an unstable equilibrium. And in the high recovery case, it's a stable equilibrium. That's very interesting. So here's the stability situation. In the low recovery case, it's unstable. So you expect if you increase a little bit from 0, then more people become infected. And in the high recovery case, it is a stable equilibrium. And if we were to include the negative side, then the rest would look like this. But I'm just not including that side because doesn't make physical sense. All right, and what about this one? So this one I only care about in the low recovery situation. So let's assume that r is less than an. Then go back here, and let me take our derivative expression here. And this time I will evaluate at I equals whatever that value was. Oh, I've got it written down there, n minus r over a. And let me see what I get. So I get a n minus r minus 2a n minus r over a. It's a n minus r minus 2an plus 2r. So that's minus an plus r, or r minus an. And let's see, so I only care about this at all when I am in this situation where the yellow dot is within the range of physically possible numbers of infected people. So that's the low recovery situation. So that's when r is less than an. So that's when this number is negative. So this will be negative in the low recovery case. And that's the only case that I care about. So negative, that refers to stability. So something like this. All right, so that is our phase line diagram. And let's draw some conclusions from this, because it's really fun to draw conclusions. This is telling you, so let's think about the cases individually, one at a time. So let's say you're in the low recovery case. So the rate of recovery is lower than whatever this threshold seems to be. In the low recovery case, there are two possible equilibria. You could have no infected people, then it will stay like that forever. Or you could have exactly n minus r over a infected people, and then it will stay like that forever. But the stability is different. If you have no infected people, then even a single infection, even a tiny perturbation to the right here, will send I careening off to the right. So this is unstable. And what happens in the long term then? Then it approaches this. So this number of infected people, which is not everyone being infected, but just some proportion of the population being infected, this is like the long-term outcome that you expect from the system. You expect that this many people will be infected. And if more people are infected than that, whether you start out with more people infected than that or less people, regardless, you expect the number of infected people to approach this number. So this is an equilibrium. It's an equilibrium according to our definition of an equilibrium solution to a differential equation, but also it's what you would intuitively call an equilibrium. The system is in equilibrium between the two forces of infection spreading and infected people recovering. So when you have this many infected people, the rate of infected people recovering naturally equals the rate of new people becoming infected. And so the total number of infected people does not change. If you have more infected people than this number, then people would be recovering faster than new people are becoming infected. So you go down to this number. And what happens when the rate of recovery is higher than this threshold? Then the stability of 0 is different. 0 becomes actually a stable equilibrium. If you have any number of infected people, then the number of infected people will fall down towards 0. So this high rate of recovery, if the rate of recovery is this high, then that's what it takes to make the world good, to end the infection. Whereas for this low recovery rate, there's always a number of infected people, no matter what you do, unless you take it to 0. So if you're in a situation where you have control over R, like maybe you can devote more resources towards helping people recover or something like that, then A times N in this model, which you'd have to do some work to figure out what A should be, but if you figure that out by experiment or whatever, then assuming the model is correct, which it's totally not, it's very idealistic, but if the model were correct, then this number A times N is what you would want to strive to get your recovery rate above, because if you did, then you will eradicate the infection. Now, one thing I want you to be thinking about when we think about like changing the rate of recovery here, as you change R, you're changing the differential equation, and you would be moving this critical point, right? Like when R is 0, this yellow dot would be all the way here at N. And as you turn the dial and tune up the rate of recovery and increase R, this dot would move to the left, to the left, to the left, until R equals A times N. When R equals A times N, this number becomes 0, and the two yellow dots collide over at 0. And then as you turn up R further, then this yellow dot goes off to the negative side. So you can imagine if we were looking at a more complicated model, and if it were still an autonomous differential equation, then you could have a phase line with a whole bunch of critical points on it, maybe a lot of them. And as you vary the parameters in your model, like R here or A or whatever, the critical points move around, and they can crash into each other, and their stability can change.